Hello friends and welcome back to VHB tutorials. In previous video we had discussed about the derivation of LMTD, that is logarithmic mean temperature difference for parallel flow heat exchanger. In today's video we will derive the formula for the counter flow heat exchanger, that is LMTD for counter flow heat exchanger. You will notice that the procedure will be same. The steps which we will follow to derive this derivation or to derive the formula for LMTD for counter flow will be same. The concept will be same. But the difference is what? At last you will find the case which we are considering for the counter flow will be different, and that case is only important for us. That why, and at last we will I will say or I will explain you that why the counter flow heat exchanger are preferred instead of parallel flow in industries. The reason behind that, it is very useful for you to solve the equations for counter flow heat exchanger and parallel flow heat exchanger in case of area requirements. So for that you have to see this video till the end. Please observe these steps which we will follow in this video correctly. If you will have any doubts, then you can ask me in the comment section, and also you can DM me on my Insta handle. And please, if you are not subscribed, then please subscribe to my channel and make sure that you hit the like button if you find this video helpful, and please share as much as you can share. Right now, without wasting any time, we will start the video. So now we will start. So you can see this is the schematic diagram of the counter flow heat exchanger, and this is the temperature versus length graph of the counter flow heat exchanger. So the same procedure we will follow. What we will do, but before that I will explain this term. This THI is the temperature at the inlet of the hot fluid, TCI is the temperature of the cold fluid at the inlet, and TCO is the temperature of cold fluid at the outlet, and THO is the temperature of hot fluid at the outlet. In counter flow we know that inlet and outlet of both the fluids are different. So if you can see, the inlet of hot fluid is on the left hand side, and on the same side we have the outlet for the cold fluid, and at the right hand side we have the outlet for the hot fluid, and at the same side we have the inlet for the cold fluid, right? That means inlet and outlet are different in counter flow heat exchanger. Now what is the procedure? That we will take the elementary area of this heat exchanger. So consider dA is the elementary area of this heat exchanger. So we know in heat exchanger we have the heat transfer. So we will write let dQ be the heat transfer rate for elementary area, right? dQ is the heat transfer rate for this elementary area. So we know that due to this dQ, due to this heat transfer rate dQ, the hot fluid will lose its heat by temperature dTH, and the cold fluid will gain the heat by temperature dTc. Or you can say, due to the heat transfer rate dQ, the hot fluid is cooled by temperature dTH and the cold fluid is heated up by the temperature dTc. Don't worry, I will write that statement on this board, but before that I want to explain some different things. So at any instant of time, suppose that at any instant of time, here we know that heat transfer is occurring. So we will consider any instant. So suppose that at any instant of time the temperature of the hot fluid is TH and the temperature of the cold fluid at the same instant is TC. So these temperatures are TH and TC. So we will have the end temperature difference theta. We will mark this end temperature difference as theta, which is equals to TH minus TC, right? Due to this temperature difference, we will have the heat transfer between the hot fluid and the cold fluid, right? So suppose that the temperature of hot fluid at the instant T is TH and it decreases to some temperature value as T-H. We are not worried about the final temperature. And suppose that the temperature at the instant T of cold fluid is Tc, which is increased by some of the temperature, and we are not worried about that end temperature. We are worried about the temperature difference. So you can see I had marked a temperature difference for the hot fluid as dTH and for the cold fluid as dTc. You can see I had written negative. Why it is negative? Because we know that in heat exchanger we analyze the heat exchanger along the length of the heat exchanger. So if you will analyze the heat exchanger along the length, then you can see the graph of the hot fluid have the negative slope along this length. We have to analyze along the length, right? So graph is negative. So for this reason I had written the negative sign. And if you can see this line, this graph of the cold fluid, then here also if you will analyze from left to right, that is along the length, then you can see the graph have the what? Negative slope. So that's why I had written negative. But if you will analyze this graph from right to left, then obviously the slope of this graph is positive. Similarly for this graph also. But generally we analyze the heat exchanger towards the increasing length of the heat exchanger, not towards the decreasing length, right? So remember that. So we got the negative temperature difference. Due to this temperature difference, that is dTH and dTc, there will be a heat exchange between the hot and cold fluid, right? So I hope you got the idea. So this is the statement, that is due to heat transfer rate dQ, the hot fluid cools by temperature dTH and cold fluid heats up by the temperature dTc, right? Now we know the energy balance equation. So what was the energy balance equation? That is the heat transfer, or sorry, the heat lost by the hot fluid is equals to the heat gained by the cold fluid is equals to the heat transfer rate of the heat exchanger. This is the energy balance of our heat exchanger, and the video on this energy balance, means the whole concept of this energy balance, is discussed in the previous videos of LMTD for parallel flow heat exchanger in the prerequisite concepts. So if you want to see that, I will provide the link in the top right corner, and also you can see the video in the playlist of the heat transfer, right? So we will apply this energy balance equation. So applying the energy balance equation to the element dA, we know that m dot h into Cph into minus dTh is equals to m dot c Cpc into minus dTc, which is equals to dQ. So what is this? This is the heat lost by the hot fluid. This is heat gained by the cold fluid. And this is the heat transfer rate of the heat exchanger, but here we are considering the elementary area. So this is the heat transfer rate of the elementary area of the heat exchanger. So this energy balance is saying that the heat lost by the hot fluid is equals to the heat gained by the cold fluid is equals to the heat transfer rate of the heat exchanger, but here we are considering the heat transfer rate of the element. So we will write the element only. Now this is m dot h is what? M dot h is the mass flow rate of the hot fluid, and its unit will be in kg per second. Kg per second. This is m dot c. It is the mass flow rate of the cold fluid, and it will have the same unit, that is kg per second. Cph is the specific heat at constant pressure for hot fluid, and its unit will be joule per kg degree Celsius or kg degree Kelvin. And Cpc is the specific heat at constant pressure for cold fluid, and it will have the same unit, joule per kg degree Celsius. And dTh and dTc, you know the temperature, it is the temperature difference. And dQ, what will be the formula of dQ? I forgot to write that. What will be the formula of dQ? So if you had watched the previous videos of mine, then you will know that the formula of dQ will be U dA into what? Into TH minus TC, because at the insta, let's say at insta t, at time t, we have the temperature of hot fluid as TH and the cold fluid at the same insta is TC. So the heat transfer rate at the same insta it will be given by, this is for the elementary area, it is given by U dA into TH minus TC, right? So if you don't know the concept behind this formula, then I suggest that you see the previous videos of mine and related to heat exchanger, right? So this is the formula which we will use. So remember this formula and mark this as formula as 1 and this equation as equation number 2, this energy balance equation. And I want you to note down these values. These are the temperature and temperature difference values for counter flow heat exchanger. And this you know. I assume that this you know, because the concept behind this also discussed in the introduction part of my heat exchanger video. So we got the formula. Now what we will do? So we know that from the equation 2 we will find the value of dTh and dTc, right? So for that I have to rub this part. So please note this part. So I can write from equation 2 we get dTh is equals to what? dQ divided by m dot h into Cph. And from the same equation I can also get the value. Here minus will be that because we have the minus sign. And from the same equation I can get the value of dTc also. So dTc is equals to minus dq upon m dot c cpc. Please observe, you will find this value only from the above equation number 2. So mark this as equation number 3 and equation number 4. So what we will do? We will subtract equation 4 from equation 3. So subtracting equation 4 from equation 3, we can get dth minus dtc is equals to what? Here we have the minus sign. So minus dq upon m dot h into cph plus minus minus plus dq upon m dot c cpc, right? Now we know what is m dot h into cph or m dot into cp. It is the heat capacity rate. So we will reduce this term as m dot h into cph is what? Is equals to capital C h. It is the heat capacity rate, right? And m dot c cpc will be heat capacity rate for cold fluid. So I will replace these terms by ch and cc, right? So this is dth minus dtc equals to minus, here minus dq will be common, so minus dq out. So I will get 1 upon ch minus 1 upon cc, right? Oh, we got this equation. Now we will do what? We know this formula. This is this, and we don't know the formula, but we know that from the graph, if you remember, our value th minus tc is what? Is theta. So if th minus tc is theta, then for small interval time dth minus dtc will be what? Will be d theta. So we can replace dth minus dtc as d theta, right? So d theta is equals to minus, I will substitute this term into u dA into th minus tc into 1 upon ch minus 1 upon cc, right? What is th minus tc? Now only I discussed, it is theta. So d theta minus u dA into theta into 1 upon ch minus 1 upon cc. Now after this step or after this equation, we know that what is the next step? We getting the variable separable form. So it is d theta upon theta equals to minus u dA into 1 upon ch minus 1 upon cc. Now this expression is for the elemental area. If we integrate this expression, then we can get this formula for the whole heat exchanger, that is whole counterflow heat exchanger, right? So for that I will rub this part. So you can write a line that integrating this equation, we will get integration of d theta upon theta from theta 1 to theta 2 is equals to what? U is constant, this term is also constant because m dot h and cph and m dot c and cpc are constant. U is also constant. Why it is constant? Why we had taken these terms as constant? I had discussed in the first video or the second video, right? Because these are the part of our derivation, that we have to assume that u will be constant, m dot h will be constant, cph will be constant, same as m dot c and cpc, right? We have to assume that. So u and this term will be out of the integration, so we will get minus u into 1 upon ch minus 1 upon cc into integration of dA, right? So it is from a is equals to 0 to a is equals to a, the whole heat exchanger. So we know the integration of this term will be ln of theta from theta 1 to theta 2 is equals to minus into 1 upon ch minus 1 upon cc into a, right? I written directly, and this will be ln of theta 2 by theta 1. This we know, right? So I will write directly ua into 1 upon ch minus 1 upon cc. Now we got this equation for the whole counterflow heat exchanger. So now we want to find what? We want to find the value of this. So from where we can find? By using the energy balance equation, and that energy balance equation we can apply for whole counterflow heat exchanger. So now applying the energy balance equation for the complete, this is the heat exchanger. So for complete heat exchanger, so we know that heat transfer rate of a heat exchanger is equals to the heat lost by the hot fluid is equals to the heat gained by the cold fluid. So this is for the complete heat exchanger. So what it is? Q is equals to m dot h Cph into Thi minus Tho. So you can see we are considering the whole heat exchanger is equals to m dot C Cpc into Tco minus Tci. Why it is not written Tci minus Tco? Because when the cold fluid enters, the temperature at the inlet will be smaller as compared to the temperature of the cold fluid at the outlet. Why? Because the heat which is lost by the hot fluid will be gained by the cold fluid, and at last it will rejected from the heat exchanger at the outlet. So at the outlet the temperature of the cold fluid will be higher. So for this reason only I had written Tco minus Tci. So I hope you got the idea. So what this is? This is what? This is heat capacity rate. That it is Ch, that is for cold fluid. The product of m dot h, mass flow rate, into specific heat will give the heat capacity rate, and this is what? Heat capacity rate for cold fluid. So I can just replace these terms by Ch and these terms by Cc, right? This knowing. Now what we will do? I have to rub this upper part. So from this equation, let mark this equation number as 5, right? So from this equation number 5, I can get the values of 1 upon Ch. So 1 upon Ch is what? It is Thi minus Tho divided by Q. And for 1 upon Cc will be what? Tco minus Tci upon Q, right? We got the values of 1 upon Ch and 1 upon Cc. Now what we will do? We will just subtract this and we will put this whole expression in this equation number 6. So ln of theta 2 by theta 1 is equals to minus ua into 1 upon Ch is what? It is Thi minus Tho minus 1 upon Cc. So it is Tco minus Tci, right? The LCM is same, so I will write Q as whole. Now if you will observe this equation carefully, then you know that Q is common LCM, so I will bring out of this bracket. Then if you will observe the numerator carefully, then you know that our theta 1 and theta 2 will come there. How? We have the formula of theta 1 for counter flow, it is Thi minus Tco, and theta 2 for Tho minus Tci. So we have to bring this expression in the above equation. So how we will bring? Just observe it. So ln of theta 2 by theta 1 is equals to minus u into a upon q, right? Now into bracket we have to do some arrangements. So we have for theta 1 it is what? Thi minus Tco. So we have Thi and minus Tco we have. So we will bring this together. So Thi minus Tco. Now what about theta 2? We have Tho minus Tci. Here we have Tci minus Tho. So we will bring the minus sign out. So minus Tho minus Tci. So now check, is it correct? So I think is it correct, right? Now what? Now we will substitute this Thi minus Tco and Tho minus Tci as theta 1 and theta 2. So we are getting a most beautiful equation, but same equation which we are getting in the parallel fluid exchanger. But difference is what? Is it the case? We will observe the case. It will be different. So here we have theta 1 minus theta 2, right? If you will bring this minus into bracket, we can get theta 2, ln of theta 2 by theta 1 is equals to ua upon q into theta 2 minus theta 1, right? Now bringing q on the one side, you will get ua theta 2 minus theta 1 upon ln of theta 2 by theta 1. This equation number as equation number 7, right? Now the last step is, now you know that the total heat transfer rate from a heat exchanger is given by which formula? It is Q equals to U into A into theta M. That is, the total heat transfer rate of a heat exchanger is given by which formula? Q is equals to UA into theta m. Theta m is nothing but our LMTD, that is logarithmic mean temperature difference. So if you will compare equation number 8 and equation number 7, then you will find the value of theta m, and theta m, the value of theta m or the formula of theta m is same as the formula which we are getting in the case of parallel flow. It is same, you can observe. So theta 2 minus theta 1 upon ln of theta 2 by theta 1, or you can write theta m as theta 1 minus theta 2 upon ln of theta 1 upon theta 2, right? So we got the same formula which we are getting in the case of parallel flow, but difference is that if you will observe the graph correctly, then the end temperature difference theta 1 and theta 2, we can take them as approximately same. Now the game starts, now the new thing starts, so just observe it. So now we will see that special case, that what is this special case. Now if you will solve the sums of parallel flow and counter flow heat exchanger, then you will observe something, that in case of counter flow, the value of theta m will always be greater as compared to the value of theta m in the parallel flow. Why it is, we will see. So suppose that if you will observe that graph, let me show here, that graph was looking like this, right? The graph was looking like this. This is the hot and this is the cold fluid line. This is the theta 1 and this is theta 2, right? The graph of counter flow looks like this. So you can observe minutely, then you will find that the end temperature difference, this theta 1 and theta 2 are almost same. Not in all cases, but we can take this end temperature difference in some of the cases as same, that is theta 1 almost equals to theta 2, right? So we will assume this as case 1. So let theta 1 is equals to theta 2. So now if you will put this equation, now let us consider this as theta. So if you will put this equation in the above, this is equation of theta m, then you will get what? 0 upon 0 form. So it is what? Indeterminate form. So we cannot put this case directly into this formula. So what we will do? What we will do? Now if your knowledge of limits of mathematics are well or good, then you can predict that we can use here what? L'Hospital rule. So for that we have to bring some limit concepts. So what it is? So we will find this formula, the formula of this case by what? The limit concept, and we will use this L'Hospital rule. So what it is? Suppose that limit. Now we are considering what? That the theta 1 is equals to theta 2 or theta 2 is equals to theta 1. They both are same. So I can write that the limit theta 1 tends to theta 2 means what it is? The value of theta 1 tends to theta 2. That means approximately they are same. We can consider that. So limit theta 1 tends to theta 2, but before that I just forgot that we have to write theta m is equals to now limit theta 1 tends to theta 2. So what we will do? We will write this equation, that theta 1 minus theta 2 divided by ln of theta 1 upon theta 2. Why we are doing this? Because we observed that by putting this case directly into the above form, then we are getting this indeterminate form. That means this is not of use. So to eliminate this condition, we are using this limit concept. Now what is the next formula? What is the next step? So the next step is we have to bring this whole equation into one variable. So how it is? I will do this. Just observe. So now we will do theta 1 upon theta 2 tends to 1. So similarly, here also I have to bring theta 2 out common. So it will be theta 1 upon theta 2 minus 1, and we have theta 1 upon theta 2 same. So we will keep this same. Right? Why I am doing this? Because I want to bring this whole equation into one variable only. Right? Remember that. So the next step would be, I will assume that let theta 1 upon theta 2 as r. So theta m equals to limit r tends to 1. Right? R tends to 1. theta 2 same into r minus 1 upon ln of r, right? Now we know what, that theta 1 is equals to theta 2 is equals to theta. So I can substitute theta 2 as theta only, because here we have the case. So limit r tends to 1, theta into r minus 1 upon ln r. Now what is the meaning of this whole? That means here r is the variable but theta is the constant. We can consider for the time being that r is the variable because r tends to 1. Now you can see, now only if you will put this limit of r directly as r equals to 1, then again you will find what? You will find 0 upon 0 form. Again we are getting this same form only. If you will put the values, then you will get 0 upon 0 form. So in limit concept, when we get 0 upon 0 form, then it is preferred to use L'Hospital rule. Now what is L'Hospital rule? That in L'Hospital rule, we differentiate the numerator and denominator separately. Just observe this. So we will use L'Hospital rule. So by L'Hospital rule, we will differentiate the numerator and denominator part separately. Limit r tends to 1, differentiating the above numerator means the numerator with respect to what? We have the variable as r. So we will differentiate the numerator and denominator separately with respect to r. So what? Observe this. Theta is constant with respect to r. So as it is, our differentiation of r will be 1 and minus 1 will be 0 because it is a constant, upon ln of r it will be 1 upon r. So if I am not wrong, then it is correct. Yes, it is correct. So now if you will put the value of r or the limit of r, you will find the we are not getting the 0 upon 0 form. So we can get the value. So putting the limit, you will get theta into 1 upon 1 upon 1, right? So we are getting the value of theta m is equals to theta. Now suppose that if you got here again 0 upon 0 form, then don't worry, just apply this L'Hospital rule again. Then after applying that, again check what you are getting. If you are not getting this 0 upon 0 form, then you have to just put the limit, value of the limit in the equation. Then your answer will be there. But normally we have to just apply this L'Hospital rule only one time. So we will get this our answer. So what was the condition? That we assume that our theta 1 tends to theta 2, or theta 1, the values of theta 1 and temperature difference is approximately same. So we are getting what? Our theta m is equals to theta. So we got the beautiful case that here in this case our heat transfer rate of a heat exchanger is given by UA into what is theta m? Theta m is theta. That is, theta is what? Theta is theta 1 is equals to theta 2. You can put any of the value from this to theta 1 and theta 2. So for this reason, the value of theta m in case of counter flow is always greater than the value of theta m in the parallel flow, right? So that was the first point to remember or to note down. Now if you want to know that why the counter flow heat exchanger are preferred instead of the parallel flow, so for that also I have the reason. So I will show what is the reason. Now we know one point, that in case of counter flow heat exchanger, our value of theta m will always be greater, right? So we will keep this in mind. So our theta m is greater in counter flow, right? This we know. Now according to this condition, we will get the condition for area, that what will be the area requirement, right? So you know that Q is equals to UA theta m. So from this we can get theta m is equals to Q upon U into A, right? So now just observe this video correctly and pay attention. We have theta m greater in case of counter flow. So from this equation, if you want theta m to be greater for constant heat transfer rate, let's assume that heat transfer rate is constant for this condition. So for this constant heat transfer rate, if you want theta m to be increasing, then what would be the effect of U into A? U will be constant, that we know. So there will be area. So theta m is what? Theta m is inversely proportional to area. So if theta m increases, that means our area requirement in case of counterflow reduces. That means the heat transfer rate, suppose that we are getting the 20 watt heat transfer rate in parallel flow by using the area 100 meter square. Suppose we are assuming a imaginary condition. What? That in case of parallel flow heat exchanger, we are getting 20 watt heat transfer rate by using 100 meter square area. Now if you will replace this parallel flow heat exchanger by counter flow heat exchanger, for getting the 20 watt heat transfer rate, then in that case you will require the area lesser as compared to the area which is required in this parallel flow heat exchanger. So what I can say, that if you are using parallel flow heat exchanger and you are getting the heat transfer rate as 20 watt by considering the bigger area, then you can replace that heat exchanger by using by counter flow heat exchanger, and you can get the same rate of heat transfer by using smaller area as compared to the area which is used in the parallel flow heat exchanger, right? If you don't understand, then don't worry, I will again explain it. So this was the condition. That means when our theta m in counterflow is more, then we know that our area requirement for counterflow heat exchanger is less. So now if we want to check about parallel flow, so in parallel flow we know that theta m is less as compared to counterflow. This is parallel flow. So what is the formula? Q UA into theta m. So theta m is what? Q divided by U into A. We know that Q is constant. That means theta m and U is also constant. So theta m is inversely proportional to area. So we know that our theta m is less. So when this theta m is less, then we have to use area more. That means if we want to get the same heat transfer rate which we are getting in the case of counterflow by using the smaller area, then if you will use the parallel flow heat exchanger for getting the same heat transfer rate, then you have to use bigger area as compared to the counterflow heat exchanger. So for this reason only the industries prefer counterflow heat exchanger more, right? In previous video, in first video, I given a rough idea, a rough intuition that why the counterflow heat exchanger are used instead of parallel flow. But the true reason behind this is this. That means area requirement. So I can write the area requirement chart. That area requirement in counterflow will be less as compared to area requirement in what? In cross flow. In cross flow heat exchanger will be less as compared to area requirement in the parallel flow heat exchanger. So from this chart you can easily solve the MCQs that the area requirement in the case of counterflow is very less as compared to area requirement in parallel flow. That means for getting the same heat transfer rate as we are getting in the case of counterflow heat exchanger by using the smaller area, to get the same heat transfer rate we have to use bigger area when we are considering the parallel flow heat exchanger. So I hope you got this whole concept in mind. If you have any doubts, then you can ask me in the comment section. You can DM me on my Insta handle, right? But remember this concept, this is important. We will solve the sums related to this parallel flow and counterflow also in the next video. So till then, have a good day and bye. So that's all. I hope you had enjoyed this lecture. If you have any doubt, then please ask me in the comment section, and you can DM me on my Insta handle. So keep safe, keep yourself safe, be healthy, be happy, keep learning, keep growing, and bye until the next video.